Hello everyone, welcome to differentiation. So differentiation is all about finding the gradient. Now let's say I have this function y equals to fx. It looks like this black curve over here. Now I take a random point at x, the y value will just be fx. And let's say I have another point at x plus h, the y value will be fx plus h. We can draw a red line between these 2 points to find an estimate of the tangent at fx. The tangent at fx probably looks something like this. If you look at this, x and x plus h differ by h. If h gets closer and closer to 0, so this gets smaller and smaller, this means we are moving the red point closer and closer to here. The line between these 2 points becomes a more and more perfect estimate of the actual tangent. Now we have a good picture of what happens when we want to find the tangent. But what is the gradient of this tangent? The gradient is just the rise over run, or the change in y over the change in x. The change in y is just the fx plus h minus fx, that's the vertical distance. And the horizontal distance, or the x, is just h. So we have it that the gradient, which is fx plus h minus fx, again that's the y, over h, again that's the x. So we have the rise over run. So if we take the limit as h approaches closer and closer to 0, basically the points become so close to each other, this will find out the gradient of our tangent line at fx. This works for any value of x. That's why we call this the gradient function, returning the gradient of the tangent at any point of x. Now let's look at some notation before we continue. This over here is what we call f prime x, or the first derivative. What this means is we are differentiating the function to find the gradient of fx. dy over dx just means the same thing. This is still the first derivative. You can also write this as d over dx of fx. Next, we can also find the second derivative. This will be more useful a bit later on in the applications of differentiation. This is what we call f prime prime x. Now we can also represent this as d2y over dx squared. The second derivative is the derivative of the gradient function. So we are differentiating this gradient function. We are finding the gradient of the gradient function. That's a bit confusing, but we'll see why this actually comes into play a bit later. But for just this video, we'll be focusing on the first derivative, which is just, again, the gradient of fx. What we learned earlier, which is this thing, is what we call the first principles. This is the most rudimentary way of doing differentiation, but it's really slow. So this question, using first principles, find d over dx of x squared. Again, we'll be learning a lot of differentiation formula later. First principles is only applied when they ask you to use first principles. Let me zoom in. Let's find d over dx of x squared. So what we're doing is differentiating x squared with first principles, or finding the first derivative of x squared. So I'm going to write limit as h approaches 0 of fx. In this case, fx is just x squared. So we'll take x plus h squared minus fx over h. Now we can't immediately substitute h for 0, so what we want to do is expand the top. We get x squared plus 2hx plus h squared minus x squared over h. And we can actually just cancel out the x squared and minus x squared. So this becomes 2x plus h. And this is the limit where h approaches 0. So nothing happens to x. As h approaches 0, the limit just becomes 2x. And that's the first derivative of x squared, 2x. Now let's move on to basic differentiation. If you have the derivative with respect to x of a is just a constant, and the derivative of that is just 0. So remember, the derivative of any constant is equals to 0. Next, this is called the power rule. If you differentiate x to the power of n, what we want to do is bring the power down, we put the n down, and then we minus 1 to the power. So if we differentiate x cubed, we want to bring the power down, we bring the 3 down, and then x, and then 3 minus 1, and that's 2. I just want to remind you that this n, this power over here, can be any real number. It doesn't just have to be integers or natural numbers. It can be fractions, such as half, or even like -1. So beware of that. Next, if you have a constant multiple, let's say you have d over dx of k times fx, we can actually bring the k outside of the derivative. So we have k d over dx of fx. Now the last one, if we have d over dx of fx plus minus gx, we can also split this into 2. This becomes just the derivative of fx plus minus the derivative of gx. So let's do this question. Find d over dx of this very long thing. From this last rule over here, we know that we can just split it up into many different parts. This is just d over dx of 3x squared plus d over dx of 2 square root x, and I just finish the rest. Now let's apply power rule. 3x squared differentiated becomes, if you bring the power down, this becomes 3 times 2, and then x to the power of 1. Next up, this is just 2x to the power of half. I like to write it in terms of power so that I can see it very carefully. If I bring the power down, become 2 times half, which is just 1, and then we have x to the power of -half, because we take half minus 1 for the power. Next, if we differentiate a constant, we just get 0, so there's nothing there. And then finally, if we want to differentiate 1 over x, if I write it in terms of powers, this will be x to the power of -1. So if I differentiate that, I'll bring the -1 down, and then I'll have x to the power of -1 minus 1, which is x to the power of -2. And simplifying this, I'll just get 6x plus 1 over square root x plus 1 over x squared, and that's my answer. Now let's go on to the next 3 rules. These 3 rules are very important to remember. The first rule is chain rule. If we have d over dx of a composite function, f gx, this will just be f prime gx, so this is substituting gx into f prime x times g prime x. Now the next rule is product rule. If we have 2 functions of x, u and v, again these are 2 functions of x being multiplied together, the derivative will just be u dv over dx, so we differentiate v and keep u, and then we differentiate u and keep v. Quotient rule kind of has a similar pattern. If we are differentiating u over v, again u and v are functions of x, this is just v du over dx minus u dv over dx over v squared. Now let's do a few questions. Find d over dx of x squared plus 2 to the power of 5. Now what we can do is use chain rule. We know that fx will just be x to the power of 5, and gx will be x squared plus 2. So if we do this, this just equals to f prime. F prime is 5x to the power of 4, but we want to substitute gx inside, so this becomes x squared plus 2 to the power of 4, and then with times g prime x. If we differentiate, this becomes 2x. So this is just 10x, x squared plus 2 to the power of 4. Now later I'll teach you a trick that you can do with chain rule to make things really fast. But first, let's do this question. Find d over dx of x squared over x cubed plus 5. So we see over here that we're just going to apply quotient rule because we have 2 functions of x. One in the numerator, one in the denominator. So this equals to v is the denominator, v times du over dx, which is just differentiating the numerator, minus u is the numerator, so we have x squared, times dv over dx, so we're differentiating the bottom. This becomes 3x squared. And we have this over v squared. V is the denominator, x cubed plus 5 squared. Now if I simplify the numerator, I'll just get 10x minus x to the power of 4 over x cubed plus 5 whole thing squared. And that's our answer. Alright, now we're gonna learn even more derivatives. We know how to differentiate x squared, but we don't know how to differentiate so many other things. Before I continue, all the derivatives that I'm giving you here on out are all in your formula booklet. So you don't have to explicitly remember them, but I think they're very good to remember. Now, first of all, if we differentiate e to the power of x, we will get e to the power of x. Wow. Next up, if we differentiate a to the power of x, we will get a to the power of x times ln a. If we differentiate ln x, we'll get a very nice 1 over x. And finally, if we differentiate log base a of x, we'll get 1 over x ln a. Now remember earlier when I said I was going to teach you a little trick with the chain rule? If you want to use chain rule with any of this differentiation formula, what you want to do is replace x with fx and multiply by f prime x. So what do I mean? Let's say I want to differentiate e to the power of fx. What I will get is e to the power of fx. Again, you're just replacing the x with fx or here, and then you multiply by f prime x. So let's say I want to differentiate ln of fx. What I'll get is 1 over, again you replace x with fx, and then you times f prime x. Alright, let's first attempt a question. Find the derivative of x times e to the power of 5x plus 2. Now you see I've conveniently written the product rule over here for your reference. If we see, this is a product between x and e to the power of 5x plus 2. We don't know how to differentiate this entire thing in totality, that's why we need to break it into two parts to use product rule. So let's do this. Let's take this as u and let's take this as v. So what we do is get u, so that's x, and then we'll multiply this with the derivative of v, which is this thing. And the derivative of that, we look up here, we are just using chain rule, where we replace x with fx in the formula and then times with f prime x. So what we get over here is e to the power of 5x plus 2, and then we are multiplying this with f prime x. We are differentiating the top part, which is just 5. And now we'll plus, and then I'm going to differentiate x, this just becomes 1, and then I'm going to keep v, and this becomes e to the power of 5x plus 2. So this is just e to the power of 5x plus 2, 5x plus 1. And that's your answer. Now we only have two more types of derivatives, the derivatives of trig functions and the derivatives of inverse trig functions. So let's go through this really quickly. D over dx of sine x will be equals to cosine x. Differentiating cosine x will give you negative sine x. Differentiating tangent x will give you secant squared x. A reminder that secant square is just 1 over cosine square x. If you watch my trig video, how I remember this is s gets switched with c, and cosecant will be 1 over sine. Next, the derivative of secant x is secant x times tangent x. For cosecant x, it becomes negative cosecant x times cotangent x. And finally, the derivative of cotangent x is negative cosecant squared x. Again, we can apply chain rule like this for all these formula over here. So let's do this question. Differentiate secant square 2x with respect to x. This over here, we know this is just secant 2x whole thing squared. Now, if you look here, I've applied chain rule to the power rule we saw earlier. So what this should look like would just be 2 secant 2x, and then we have this as to the power of 1 times the differentiated value of secant 2x. So differentiating secant 2x, we see here, would just be secant 2x, tangent 2x, and then times the differentiated value of 2x, which is just 2. Now again, when it comes to chain rule or anything to do with differentiation, the most important thing to do is practice, because after you do a lot of practice, you'll be able to do all this without even looking or writing down the formula. Now let's look at the last set of basic derivatives. We have the derivatives of inverse trig functions. So differentiating arc sine x with respect to x, we get 1 over square root 1 minus x squared. Differentiating arc cosine x will give us a negative of 1 over square root 1 minus x squared. And the final one, the derivative of arctangent x will give us 1 over 1 plus x squared. So this question asks us, find the gradient of y equals to arctangent x at x equals to 3. We know that dy over dx equals to 1 over 1 plus x squared. What we are doing with dy over dx, or differentiating, what differentiating is all about is finding the gradient. So dy over dx, or f prime x, will give us the gradient function, which is the gradient at any point of x. But specifically, if I want to find the gradient at x equals to 3, I can write dy over dx when x equals to 3 is just equals to 1 over 1 plus 3 squared, and that is 1 over 10. So that's your gradient at x equals to 3. You can also write this notation as f prime of 3. Now here's the summary sheet for all the differentiation techniques. Thank you so much for watching. I hope this video has benefited you greatly.